things we did back in 2010 and 2011. And so that kind of concludes the frustrating part of my talk, where I can just tell you about high-level results. The next thing I'd like to do is to dive a little bit deeper into what we do now. I guess before I do this, the one thing I want to say, which I think was very satisfying for both the students and the staff overall, the whole project, is that, you know, if you look at all the major players in the field, we have interacted with almost all of them in any capacity over the last 4 and 5 years, and that's very satisfying because this field is very mature. It's mostly migrated to the private sector, but either way you look at it, this was created in partnership with Nokia, Naflec, and Telenav. They actually funded this work, and so it was implemented in their system directly. And even though we couldn't work with Google directly at the time because Nokia had 40% of the market share, and these were really competitive times where the two companies couldn't be working together, now we do, because the situation with Nokia has changed, and so now a lot of my students, in fact some of them work at Google Zurich, where the traffic operation is run, and these algorithms are in the process of being implemented and tested on Google data. And the other companies, like the ones you can never work with, like Apple, because of secrecy, have hired our students or former staff people to basically build that for the iPhone, the latest release of the iPhone. I don't know this because nobody knows what my students are doing at Apple, but I think that's what they were hired for, and certainly, and they can't tell me, and of course, and same deal with Microsoft. And so I think the reason why I'm showing this is that I think this is a very nice example of how something which was started in 2007, which was not even thinkable, is now a complete commodity and run across the private sector. Now, where are we going with this now? So now, you can pretty much see anywhere in the world. I think Google traffic is deployed in 72 countries already. You can pretty much see traffic everywhere in the primary and the secondary transportation network, so not in the rural roads, not in the, I would say, residential streets. And that means you can probably access a lot of people there, and you can try to figure out how to use this to route people better through the network, and that goes into what we're doing right now. So the next thing I want to do maybe in the next 10, 15 minutes is to take one algorithm for routing we've been working on for the last couple of months, and explain how we would use this in the context of social networks and how you could incentivize people to do something which is better for society as a whole, i.e. try to equilibrate traffic among different road network links. So the idea is you want to use that information to redistribute traffic in a more optimal way. And the setting we've chosen, unlike in the previous part where we really put it to practice, we had to deal with the dirtiest model and data there is, this is still idealistic, and there's still a lot of theoretical work before we can reach the same level of maturity. You will see it in the models, but the point is you have to understand the simple case before you do the real thing. And that was the same with the first phase historically as well. So here the situation we're looking at is simpler. We have two cities, say San Francisco and San Jose, and you have thousands of people commuting from one to another every day. And typically, you only have 4 routes, really. You have 280, 101, and if you're crazy, you could cross the bridge and go 880, and if you're really crazy, you could go 680. But the point is, there's only 4 ways to go from one to another. So in terms of network analysis, it's a parallel network, and you're trying to route a certain amount of flows and allocate that amount of flow between the different links, and try to minimize the overall cost function, which encompasses the total travel time of everybody involved. Okay, so you have a latency function, which is the time to travel on the link. You have a flow, and the total time spent on the road on that link is the amount of flow time, the time it takes to travel the link. It's a static problem formulation. There's no dynamics there. And you try to minimize this for all of the network. Now, the game is, if you give people information, they'll route themselves differently. If you give them rewards, they'll route themselves differently too. You could incentivize people to take a different route for a coupon, for a free cappuccino at the local Starbucks if you have a partnership, or for any kind of reward. And if you have the right incentivization model, they do this in Singapore, they do it in lots of different places, and you can do it through apps, through information distribution and many other things, then you can start to route people as you wish. And that's where the field is going, and that's what we're interested to do. And then you can compute what's called the price of anarchy, which is the cost of a Nash equilibrium, which is the cost of what happens is if everybody behaves selfishly, over the cost of the social optimum, which is what would happen if people followed what they were told, and that means some people will take a longer route so that society as a whole benefits. That's called the price of anarchy. And so what we're going to try to do now is to see first how to quantify this, and then how to create a Stackelberg game on it, which means now if you could control a fraction of the population, how should it be controlled in a way that society benefits as a whole? So the notion of a Stackelberg game here is relatively intuitive. It fragments the population in two categories. The first category are the people who are going to be selfish and are going to try to do what's best for them no matter what it does to society. And the second fraction of the population is going to be what we call compliant people. And these would be people who would be ready to take a reward, to take a little penalty on their commute. So I'm ready to take $5 or a lottery ticket or a free cappuccino to waste an extra 10 minutes of my travel time, or to take a route which is 10 minutes longer. So you have a total flow amount of R that you're trying to push through the network, and you have a proportion alpha, say 2%, 3% of people, that you're going to route differently. They're going to do something good for society. And you have the proportion 1 minus alpha, the rest of the people, who are going to do the selfish thing. So you call S, that fraction of compliant people, and you call T of S, the reaction of the non-compliant people, the people who are going to readjust themselves selfishly based on what the good guys do. The good guys or bad guys, different terminology. And what you're trying to do as a planner is to optimize the overall travel time of the compliant and the non-compliant people altogether, given that you can only control the compliant people. Sorry, this is annoying. I don't know what's happening. My computer doesn't like the wireless here. I don't know why. If you can compute the best such equilibrium, well, that's what's called the optimal Stackelberg equilibrium, and that's the best thing you could do as a society if you could only control a certain fraction alpha, 2%, 3% of the people. And the interesting thing is that in internet routing literature, that problem is actually NP-hard. And that's because the latency function on the internet has a very specific form. The latency function in transportation is actually much more complicated, but ironically, that makes the problem polynomial time solvable, which means in our case it's really good because it can be solved very quickly. So going back to my latency, we saw this in a couple of slides ago. You know, the flux of traffic on the freeway increases linearly, or some ways, as density goes up. And at some point it starts to go down, and if you get there, you're really packed on the freeway and you're not moving, technically your travel time can become infinite. What that means is that if you look at this triangular shaped diagram, and it also works with untriangular, but that's a bit more complicated, you have free flow, you have congested, and if you look at the way your latency changes, the more density, the way the latency works, initially it's flat, right? Because whether there's a few people or a bit more people on the freeway, people all go the same speed, roughly the speed limit, so the latency is flat. But at some point, when traffic starts to increase, then latency goes up very quickly, and if you're stuck on the freeway, technically your latency goes to infinity. So that's the latency function we have. It's very different from the internet routing literature, because in the internet routing literature, the shape is quite different. The interesting thing is that this is actually not a very useful way to plot it. What you really want to plot it is as a function of flow. As a network control person, I like to push flow in the freeway. So I'm looking at that latency function as a function of flow. So it's the same graph as before in a different coordinate system. So if you push more flow initially, it doesn't change the latency. It's uncongested, m equals 0. But if you push more flow, at some point you reach a congestion point, and if you try to push more people, actually you decrease the flow in the freeway. And that's like more and more people want to go on the freeway, but the flow actually decreases, so your latency goes up, and that's a multi-valued function. And we're going to use it this way because that's the way you can characterize Nash equilibria in it. So maybe now is the time to stop me if that function is unclear, because if this is unclear, everything else is going to be incomprehensible. But that's the main tool we're going to use here. And that latency function is very closely related to that fundamental diagram. It's just characterizing the fact that if there are too many people on the freeway, then latency goes up really quickly because you're not moving. Okay? So,
I have a question.
Yeah.
Does your approach rely on the triangular assumption, or does it just need to be concave?
Right. So in terms of the PD to be post, all you need is concavity. But if you have a nonlinear portion of the fundamental diagram in the free flow, that part will be flat. And the notion of Nash equilibrium, which will be much harder to define, for a reason which will appear very clearly in 3 slides. Now that part could be anything you want, as long as it's concave, but it's very useful to have a linear part here. So, I think the general concave part is still something we need to figure out in that context. So you need to make some assumptions, like the one I just mentioned. And now let's think about what a Nash equilibrium means for that system. So in a Nash equilibrium, everybody behaves selfishly. There is no incentive to switch path, because that's the way it's defined. And what that means is that if you have several roads chosen by the people, so first road is really fast, first road is really fast, second road is a bit slower, third road is even a bit longer, in a Nash equilibrium, everybody's equal. That means the latency, whatever it is, say 30 minutes of travel time, if you're on that road, you're going really fast because you're a free flow. That's because the road is very long, but you're going fast all the time. So this is someone like me who would want to go on 280 really fast and never be stuck in traffic. At the end, you still have the same travel time as if you're on this road where you're really packed. You go for a shorter distance, but you're really packed all the way. So Nash equilibrium looks like this. Everybody's equal, and each of the points here represents the flow, and everybody has the same latency. Okay? So that's what happens when everybody behaves selfishly, and all road links which are used, which have a non-zero flux on a horizontal line, here, for example, the fourth road is not used by the users because the flow doesn't require it, and everybody has the same travel times. That defines a Nash equilibrium. So the way that works is basically, initially you have a small amount of people. The more people, the more flow. At some point you saturate the first road. What happens next is then people start to move to the second route. So now you basically accommodate people between the first route here and the second route, and the total amount of flow starts to rise, and you continue rising the amount of flow, and you continue filling that diagram. Now the third road has opened, and so on. That's how these Nash equilibrium progressively fill the freeway, and if people behave completely selfishly, this is what you would see on parallel road networks. The beauty of this is that you can show that a Nash equilibrium has a very specific property, which is either all its links are congested, or there's at most one link in free flow. You can show this, and the nice feature of this is that that means you can enumerate this Nash equilibrium. There are two n of them, where n is the number of links, and that's good because in proving that you can solve the problem in polynomial time, all you have to do is to enumerate for these two n Nash equilibria, and that's the reduction to p of that problem stems from that property. Now, what does that mean? Say, if I have one of these links, that means that everybody's going to be congested, except at most one person. And if I think about the amount of flow I could push in that system, then it would amount to say, well, I can be in that context until this guy moves all the way to this point, until at that point I have to move up one level. Okay? Which is what's encoded by that formula here. And it's saying that the most you can push through that system is these Q hats here, which are basically these points, and then the last guy is really the flow you're trying to push on this minus the sum of all the others. Okay? And when you exceed that amount, then you have to move one level up. So that's what happens to push as much flow onto that situation until you move up. And you can characterize that maximum flow you can push through this selfish behavior analytically, and that's part of the solution we provide. Another thing which is interesting to prove, which helps understanding how you can route people, is that you can always show that you can make things better by moving down, and depending on the properties of the latency function, you can prove that moving down is always a good thing, which means this is a case where you have a Nash equilibrium, but that Nash equilibrium is not optimal. So among Nash equilibria, some are better than others, and there is one which is always better, and you can show that for the one which is always better, you have at least one flow which is uncongested. And that's another thing you can prove nicely. So now, what are we trying to do here? We're trying to sort among all the different selfish strategies of people and try to figure out the best one, which means basically computing the argmain of the cost function. It's like among all the possible travel time allocations, if everybody behaves selfishly, and there's many ways to behave selfishly, you're trying to find the best one, and that's called the best Nash equilibrium. And you can show that the computation of that best Nash equilibrium can be done in polynomial time using the enumeration procedure that I've shown before. So now, what about people? What about routing people differently? And that goes into the Stackelberg part of this work. Is until now, everybody's behaving selfishly. You can't control anybody. So now what if we could control 2% of the people, or 3% of the people, by convincing them to leave work later or to use another route? How would you control these 2 or 3% of people in a way that overall society benefits and reaches an optimal? So that's the Stackelberg game I was mentioning before. And in that context, there's R amount of flow, and you incentivize alpha times R to do the right thing for society, and you look at what happens when the other parts behave selfishly. So that's called the Stackelberg game, because you have a leader set, that's the people who can reroute, and you have a Nash-induced equilibrium, which means everybody else behaves selfishly. So there's a Stackelberg-Nash game. And so there's N links, there's R flow, and there's alpha % of the people you can route in this manner. And then you're trying to find among these Stackelberg equilibria, which one is the best one, and that's the Armin formula I'm showing. So it turns out that there is something fairly intuitive that does work in that case, which is called the non-compliant first strategy. And the idea is that, if there's 98% of the population you cannot control, you should compute what they would do naturally first, and then fill the rest of the network in a way which is the least damaging possible for society. And so it's a very simple thing. Like you can explain this in an elevator pitch. You probably need 2 floors to explain this, but it's very short. So that non-compliant first strategy happens to be optimal and computable in polynomial time, and that's what I'm going to show next. So what does that mean? That means that you can compute the optimal Nash-Stackelberg solution by enumeration of the 2n Nash games, and showing that among these, with the alpha reroute, there's one which is optimal. So let me illustrate this graphically. If there's 3 flows of selfish people, so forget about the good guys. These are the bad guys. And so here there's k, so let's say 3. What they're going to do is they're going to do the worst thing possible. They're going to try to be selfish. And what that means is they will all have the same latency, because that's the Nash equilibrium we showed before. That means the latency will be on that line. And 2 guys will be congested. This is the fastest route, but it's packed, so you're going slower. This is the second fastest route, but you also go slow because people are congested. And then the third guy has a much longer route, but because it's uncongested, it still takes the same amount of time. So that's the bad guys. And so the idea of the non-compliant strategy is to say, well, the rest of the flows, the people I can actually control, will be filled additionally, but not equally. So for example, I need to put more flow in, so I'm going to put it here. And so far, everybody's still equal. But then when the next guys come in, instead of having everybody suffer, I'm going to just make these guys suffer. So this guy will actually go to the next road, which is much longer. But that doesn't affect the other, who are partly good guys and partly selfish. And what you do is you keep filling the network until you fill all your flow. And when you reach that point, that means you have now filled all your flow. Part of your population is controlled. These are the blue guys. Part of your population is uncontrolled. Okay, so this is controlled. These are the good guys. This is uncontrolled. These are the selfish guys. Not everybody is equal. This guy has a much longer travel time. That's why you should pay him, because you should incentivize him to take the penalty. And these guys, are selfish. You shouldn't pay them. And these guys are really lucky because they're being paid for doing the thing which is the best. So that's probably what you want to be. Basically, you're being paid for doing nothing. You can show that this strategy is optimal. And you can show that, of course, you do it reverse way, right? First, you tell the compliant guy, go this super long route, go this long route, and go this route. And then you let people adjust themselves selfishly, and that gives you this equilibrium. And that's the solution of the Nash-Stackelberg game. That can be computed in polynomial time, and that's mainly due to the form of that latency function. So that's the statement of what I just said with the figures, and I don't think I'll go here now. There's some robustness with this. You can show that you can perturb this in some ways, and as long as the perturbation doesn't exceed bounds, which can be characterized as a function of the capacity of the network, the solution doesn't change. I'm going to skip this. What's interesting, and I'll finish this and then just maybe expand the scope a bit to the end of the talk, is you can compute things which are quite interesting, such as the price of stability, which is the ratio of what would happen if only a portion of people comply versus if everybody complied. Or you could compute what's called the value of altruism, which is what would happen if a portion of the people comply as opposed to nobody complies, okay? And these ratios characterize, in a sense, how damaging your selfish behavior can be on the network. So going back to that example I showed initially, if you have these 4 routes, this would be 101, that's the fastest, 280 is almost as fast, 880 is much longer because you have to cross one bridge, and 580 is crazy because not only you have to cross one bridge, but you also have to go over the mountain. So that's fairly understandable. So now if you try to route people through that network, and then you progressively increase the flow from San Francisco to San Jose, that's the type of graphs you get. So this is a depiction of the price of stability as a function of demand. So nobody on the freeway, lots of people on the freeway, this must be number of vehicles per lane per hour. And then this is compliance, so nobody complies, everybody's selfish. And then this is a dictatorial state where everybody's doing what they're told, okay? And so what you can see is pretty intuitive. The price of stability can only increase with decreasing compliance, okay? It's always bad when people don't do what you tell them. And it's always better if they do what you tell them, and anything in the middle is fair game. And now, in terms of demand, the more demand is not necessarily means that the price of stability increases. It does by jumps, but because it's a ratio, sometimes with networks you have more flow allocated, so the ratio doesn't necessarily increase. The travel time always does, but the ratio doesn't. So this curve is fairly intuitive, and of course, if you're a dictatorial state, that's where you want to be. If you're Berkeley and nobody obeys to the rules, that's where you are. And here is a place where there's no vehicles. So you can kind of map this. And you can plot the reverse, which is the value of the altruism. And you have the same deal. Basically, if you increase demand, the value of altruism goes down. These names are a bit misleading, by the way. We didn't choose them. And then same deal, you can only